So again, in concentric brace frames, dissipation of the energy is going to happen in the braces. Whether it's going to be intentional compression, we're going to put the structural steel member beyond the yield point, and this is how you're going to be dissipating the energy. When it comes to eccentric brace frame, like in this case, the linked beam itself is going to be exposed to shear yielding, and this is the way that we dissipate the energy in this structural system. And in moon frames, dissipation of the energy is going to happen at the plastic hinge, and the plastic hinge here means the end of the steel beams. So in each steel beam here, in each bay, you're going to have two locations. This is going to be one, and here's a second, another one here, another one here. So in a case like this, you're going to have here 4 times 2, you're going to have maybe 8 plastic hinges in one moment frame. Also, we discussed this P delta effect. We say it's going to be critical, and this is actually a very good point to discuss or to ask you maybe through a quiz or maybe through the midterm, even maybe through the final. We discussed this pre-inner storage earthquake, the connection, and at that connection. Hold on. In this connection here, we have direct weld between the beam flange and the column flange, which is not good because maximum moment is going to happen right at this location. I understand that this is going to be the center line. So if this is going to be the center line, the location of the connection is going to be right here because the column itself has some dimensions, which means this moment value from here to there is going to be the maximum moment ever that you're going to have through the beam. And at that point here, you're going to be exposing this weld. And don't forget that the weld is going to be very brittle material. And all of a sudden now you expose it to high strains and stresses. Why do I say high strains and stresses? Because the stress is going to start to be constant. At certain point, it's going to be at the yield stress. And then the strains is going to be going beyond the yield strain. So in a case like this, we understand that this here a brittle material, and it's not going to be able to take all of the strains that you're exposing your steel moment frame to. So in a case like this, you're going to see lots of fracture, and all of a sudden now you don't have the connection working the way you want it, because the resistance that you're getting out of here, out of this moment frame, when you push it, is going to be based on the strength of the connection between the beam to the column. But here, if you fracture the weld, now this becomes a true hinge. And a true hinge means there is no resistance at all for any moment that you apply to it or any lateral forces. The situation that we have here, if you are able to develop a plastic hinge, it means that once you reach a certain level of force, I'm going to take you back here to one of the slides, lateral force resistance, which means right here. So if you fracture the weld, your performance curve is going to be like this. It's going to be right here. So after you go all the way to here, right, what's going to happen once you reach the yield point and you fracture the weld, it's going to drop down like this. It's going to be something like this. So performance curve is going to be reaching the yield point. After that, the strength is going to be dropping all the way down. This is especially when it comes to lateral forces and moment in the frame, because you lost now the connection from the flange to the flange of the column to the flange of the beam. So what you wanted to do is just keep it flat. You don't want to lose the strength, because the loss of the strength in this case means collapse of the moment frame system. You don't want this to happen. So what you'd like to do is to have it working at least something like this. And once you hit the elastic, I mean, once the system is going to start to gain some strength again, you want it to happen. But doing this means the system is totally gone. It's not going to be this line. It's going to be this line here. So you don't want this to happen. Going back to our moment frame. So I'd like to see a plastic hinge in each one of these locations. This is what I wanted to do. But I don't want the plastic hinge to happen at the end of the beam, because this is really just welded material. You don't want this to happen to it. This could be the pre-north bridge connection, just pure connection. You have direct connection here between the flange to the flange of the beam to the flange of the column. So what you'd like to do, either to add a cap plate, you see this cap plate top and bottom, This is to make the section itself of the beam is going to be stronger, or to cut a little piece of the beam. This little section of the beam, you cut it top and bottom of the flange. So you keep this section of the beam, this section here, or this area of the beam, to be stronger than this area here. Meaning, if I like here to put some sections and give it some numbers, so I'm going to be calling this to be section 1. So what's section 1? Section 1 is right at the center of the column. Where is section 2? I'm going to say section 2 is going to be at the face of the beam. It's going to be here. Face of the column, start of the beam. Section 3 is going to be right here. This is going to be section 3. Now, where is section 3? I'm going to say section 3 is going to be at the center of this cut. Now, let me carry all of this down. Can I show them here? In this location. Now, where is the center of the column? I'm going to say it's going to be right here, which means a grid line, right? It's going to be the section of the column, center of the column, center line of the column. How about section 2? I'm going to say section 2 is going to be right here, interface between the beam to the column. How about section 3? Let's say section 3 is going to be right here, the center of this cut. Now, if I have my moment diagram and I'd like to take the same sections and show it in the moment diagram, so let me go back here. Here's the moment diagram. Where is section 1? You can say section 1 is going to be right here at the center of the column. Now, where is the face of the beam? Face of the beam or face of the column is going to be right here. You can say it's going to be right here. You see this red line that I draw? It's going to be this line, which is the face of the column. How about 3? I'm going to say 3 maybe here. So I can throw these lines here. So this gives you the center line of the cut. And this line here is giving you the center line of the column. So actually the moment, if you're going to be modeling this through a software like SAP or whatever, or any other software, you're going to be reading, it's going to be right at the center of the column. But this is not really useful. This moment here at the center of line of the column is not useful. And here's the reason. Look at this moment here. How much is the depth of the beam resisting this moment at section number 1? Can someone help me? Yes?
Can you ask that one more time, Professor, please?
How much is the depth of the beam, right, for the moment at section 1 that I need to consider? Here's the beam depth here, right? Let's say this beam depth 24 inch, just for sake of discussion. Do you have an estimate for the beam depth at section number 1 if I have the moment acting on it? Can you help me, Mike, with this?
I'm trying to think about it, Professor.
Yeah.
Are you saying that it would be the depth of the column?
The height of the column, isn't it, Jonathan? Don't you feel it should be the height of the column?
Yeah, in that
When
direction.
I consider the moment here, I should consider the total depth or the height of the column, correct? Because look at this moment here. Look at this moment from this diagram, right? This moment is going to be at section 1. At section 1, the center line of the column. So I cannot really use this moment at section 1. It doesn't make any sense because there is no beam in this location. It's going to be the depth of the column, and the column height is going to be maybe a couple of stories, maybe 30 feet, right? So it doesn't make any sense to use this moment at section 1. I'm going to say, how about section 2? I'm going to say, yes, section 2 makes sense. The depth here, just for sake of our discussion, it could be maybe 24 inch. How about section 3? It is also 24 inch. How about any other section? I'm going to say 24 inch all the way till you hit the next column. meaning when you come here from this column to this column, right? So once you get here to the column face, which means roughly is going to be from here, right? After this point, you have the column width because the column goes from here to there. So this area here, which means a column depth, if you want to call this the column depth from this line to this line, right? You cannot really use a moment there. So this moment is not used, all of these values. You don't need them. You just need to have the moment at the face of the column. This is where you start to have your business and your analysis. So I said, okay, good. So I'm interested here in sections 2 and 3. This is what I have. I said, okay. So I have here section 2 and 3. This is what I need to care about. I have a problem here with this section 2. If this is going to be the highest moment throughout the beam, and this is true based on what you have seen here in this diagram, the highest moment is going to be at section 2. So section 2 is going to start to go in the yield, right? In the plastic performance before section 3. Do you guys agree to this?
Yes.
Okay. So I don't like that. I want section 3 to yield before section 2. So how this going to get done? And what is the measure? I mean, how would I know which section is going to be yielding first? I guess
Wouldn't
what I
you-
need. Yeah, go ahead.
Oh, wouldn't you pre-plan that one to yield first?
How would I do this? How can I confirm this? How can I force it to happen? So the way it works, that I need to find out something that we call here demand to capacity ratio. What is demand to capacity ratio? It says here DCR, as you see it here, DCR. What is DCR, demand to capacity ratio? For each one of the 3 sections. What sections? I'm going to be talking about sections 1, 2, and 3. Right? For section number 1, it is not really useful because it's going to be going through the column. So I'm going to say this is not really important, right? I can just take this out of the picture. But for section 2 and 3, it's going to be important, isn't it? So how is it going to be important? And what is this demand to capacity ratio? Demand to capacity ratio at any section is going to be equal to the ultimate moment. And the ultimate moment, of course, is going to be according to the load combination that you have in the code, divided by the moment capacity of that specific section. Whichever is going to be reaching 1 first, this 1.0, right, is going to be the one that's going to start to yield. Does it make sense?
Yes, Professor.
Yeah.
Yes.
So looking at this 3 sections here, it means I'm going to have a demand at 0.2, demand at 0.3. Correct? Because section 1 is out of the picture. As we say, it's going to be going through the column. So if I make section 3 weaker in terms of field demand, if I'm going to make this section to be weaker, which means this field demand number 2 is going to be much smaller than the ratio of M sub U1, or let me rephrase it, because as we said, we're just going to be taking this out of the picture, right? So let's work here on 2 and 3. So what we are trying to do here is to make 3 weaker than 2. And once we make 3 weaker than 2, it means 3 demand to capacity ratio is going to be reaching 1 before demand to capacity ratio of section 2. Here we go. Look at this section here. Here's 1, 2, and 3. 1 is going to be at the center line of the column. 2 is going to be at the face of the column. 3 is going to be at the center of the cut. Let me just call it here the cut for now. Here is the frame elevation. And this one here is going to be MU1. What is MU1? This is going to be the moment right here at this location, which means this moment, right? This moment. location is giving me some hard time. It's gonna be this moment here. About MU2, MU2 is gonna be this moment here, right? Right here. About MU3, MU3 is gonna be the moment right here at this section, right? At the center of the cut. So I have you 3 moments. As we said, this one is not critical because it's gonna be going through the column. This one here is gonna be important, and this one also is important because we don't want the hinge to start here. We want the hinge to start here, which means we are trying here to push or relocate the plastic hinge, right? From this location 2 to location 3. And my only chance to do this is to come at this demand to capacity ratio and start to reduce the capacity of it. Yes, I'm gonna be going back here to this. If this here is very small compared to this, what's gonna happen? This section is gonna be yielding before this, but I don't want this. So what I wanted to do is to reduce VMN3. How can you reduce VMN3? By introducing a hinge at this location. So what I need to do is to come here and cut a section of the beam. Once you cut a section here of the beam, VMN for this section here is gonna be smaller than VMN for section 2. So when you cut this section at this location at section 3, demand capacity ratio of section 3 is gonna be reaching 1 before demand capacity ratio of section 2. And with that, the hinge is gonna be relocated from the face of the beam to this location, new location that I'd like to push the hinge to. Same thing when I go back here to this diagram with the cover plate. The cover plate, its location here, or adding this cover plate is not to increase the wall thickness. It is mainly to have stronger section of the beam right here. So when you have a stronger section at section, now let me call this again, I'm gonna be calling this gonna be moment 2, and this here is gonna be moment 3. I'm just changing this little bit, right? Now what's gonna happen? When section 2 is gonna be stronger than section 3, what's gonna happen? You are gonna be forcing the demand to capacity ratio of section 3 to reach 1 before section 2. And when this happens, the plastic hinge is gonna be forming right here. Which means this moment that you're talking about, M2 and M1, will never happen. So in reality, the moment diagram is gonna be like this. It's gonna be just reaching M3, and after that, the moment is gonna be flat. There is no increase in the moment value. Because when this is gonna start to hinge, there's gonna be just lots of strains and no change in the moment through the beam. And with that, I was able to control the plastic hinge location. Any questions?
Professor, I just have a question.
Yes.
I've been wondering why the beam has that radius cut at section 3.
Yeah. This is the reason. The reason that we cut it here to make this section weaker in the strength.
Oh, okay. So it gives so that we have a ductile failure at section 3 before a brittle failure at section 2.
Yeah, you want, this is not, yeah, the brittle failure here is going to happen at section 2 because you have the weld. If you look here, I may enlarge this a little bit. Look at this, you have the weld here. So you don't want this area here to be the location of the plastic hinge. So you weaken this section. So that pheme N of this section is going to be smaller than pheme N of the entire beam, right? Especially this location. It's going to be section here too, right?
Yes.
So here's section 2. I may add it right here. I'm going to say here is section 2. And this one here is going to be section 3, right at the plastic hinge. Now, where is section 1? It's here in the center of the column, which means right here. So this moment here will never try to resist it because you have the total depth of the column or height of the column.
Yes. So
I have,
oh, I'm sorry, go ahead.
no, go ahead.
I was gonna say, so when we weaken section 3, and with the DCR ratio,
it's gonna be more than 1. It's gonna be jumped to 1 before section 2.
Yes. So that means that if section 3 fails, the system would show a ductile failure, and that's
it's not gonna fail. It's just gonna yield. I don't want to use the term here fail, because fail means that it's not even able to resist the strain.
Okay.
Like what happened, for example, if you have a 2, if you go here beyond the yield point, you're gonna have fractal failure here. So in this case, we call it failure. But this here, we're gonna call it post-yielding, or we can call it plastic performance if you want to.
Okay.
All
Yes.
right.
And
Very
for
good.
the other beam, what are the bolts in the plate
This
holding?
one,
Yes.
this one here, this can be for the shear force. Because don't forget that you're gonna have a shear force here. You have loads coming to the beam that you need to support it by direct connection between the beam to the one frame column. So this here is gonna be for the shear force. And the shear force here is gonna be resulted from the gravity load, dead load, live load, and also from the seismic forces.
Okay. And this
Right.
is only connected to the beam and not to the column, right?
This plate
Yes.
is connected by bolts to the beam and it is welded to the column.
Okay.
So this here welded to the column, right? You see the plate, the shear tab?
Yes.
It's connected to the column by welding and connected to the beam itself by bolts. So when they ship the column comes with the shear tab 6 out of it. Now they start to bring the beam, put it in, put the bolts, and then after that you weld the top and bottom flange the way that you see it here. We
Okay.
call this gonna be full pen. You see this? Or complete penetration,
Okay.
like this symbol here. All right, now let's look here. Here's the shear tab. You see how it is welded? Here's a
Yeah.
weld line, and then it has some bolts. So again, the column comes with the shear tabs 6 out of it. Then you bring the beam, you put it in, put the bolts. Now the system is ready for welding top and bottom of the flange.
Yes. And it only helps with the shear of the beam only, not the column, right?
Yes, this is gonna be for the shear of the beam, right? From gravity and seismic force is gonna be resisted by the bolts and this welding line.
Okay. Thank you very much.
No problem. Yeah,
I
John.
have a question too.
Yes.
So you said that the moment about axis 1 doesn't matter because it's acting on the full
Yes.
length of
Yeah.
the column, but wouldn't it act in the other direction because it would give the moment about the centroid of the column? Wouldn't it compress one of the flanges and put tension on one of the flanges?
It's gonna be the same thing. Now, okay. This moment here that you're talking about, we are interested in this moment to design the beam.
So
We're gonna have moment
we
on
would
the
have to
column.
worry about that in the other direction.
Yes. So whether it's gonna be coming this way or that way, just the moment it's gonna get flipped. You know what's gonna happen? Instead of having it this way, it's gonna be coming like this. Right? You're just gonna mirror it. Now, moment on the column is gonna be a different story, right? We're gonna be taken from the moment on the column, from this diagram here.
Okay.
Okay. All right, very good. Now let's talk here about the building system itself. We have, when it comes to structural steel buildings, we have 3 types of buildings. The first one here is called building frame system. Here's a plan view. I have steel columns. And of course, I have some framing. So what does it mean by framing? Framing means beams and metal deck and concrete slab on the top of it, like the system, like the composite beams that you are used to. So what's important in this system? We have columns. And then we have some brace frames. This brace frame, it could be eccentric or concentric, it doesn't matter. So if you have brace frame, concentric or eccentric, we're gonna call it building frame system, like in this system here. So when the force comes in the X direction, now this is gonna be the X, this is gonna be the Y. We have here the force is gonna be called Vx from the seismic. And we have 2 brace frame to resist it, like BF1 and BF2. If the force in the Y, we're gonna have BF3 and BF4. Look how we show or how we draw here the brace frame. You see, it's gonna be a line, here's a column, and the arrow is gonna be pointed this way, which means you have a hinge here. The brace to the column connection is gonna be hinged. Keep this in mind. We have another system that we call here moment frame building. So what happens in moment frame building? You're gonna have columns, you're gonna have moment frames in both directions if you like. So now look how we show here the moment frame connection. This is gonna be opposite. So if you do the arrow this way, the arrowhead is gonna be this direction. It means it's gonna be a moment connection. Let me show also how I showed it in the past previously in one of the slides. Look at this. You see when I showed here the moment frame? This means a moment connection. We're going to be able here to transfer the moment from one side to the other side. So I guess now we have a good understanding how to draw here the beam and the connection on plan. Let me also do something here for quick. In your project, look at the moment frame connection. This is a moment frame, right? Look at the arrow direction. Look at this. It means that you have moment connection, moment connection. It says here, size of moment frame. How about this? How do you feel about this? Is this a moment frame?
No.
No, it says EBF, eccentric brace frame. So I have here an EBF eccentric brace frame. You have one here, you have one here, you have one here, which means you have here two bays of eccentric brace frame. Let's give you two bay eccentric brace frame. Also, you have here two bay eccentric brace frame. How about in the y direction? How many you have? Let's say we have one in the y direction. We have another one. We have two. And then we have three. How about the moment frames? How many moment frames do we have? You see, I have here one moment frame. You see this on the top, on the bottom. So for the x direction forces, I have two moment frames. Each one's gonna be two bays. You see this? In the y direction, I have one coming here and one coming here. Right? Again, two bay and two bay. And here's the column. And then between you have the framing. We call this the framing. You have lots of beams and girders and things like this. So okay, good. So we have two systems again. I have building frame. In a building frame, you don't have a moment frame. So when you have a building frame, it's gonna be all EBFs, all CBF, like concentric brace frame. So in building frame, you're gonna have either eccentric brace frames or concentric brace frames. In moment frames, you have only moment frames. Look at this, only moment frames. So you say, how about this system here? What would you call this? Because in each direction, I'm showing EBFs with moment frames. So I said, well, I don't have a name for it yet, but I want you here to look at this. Look at the x direction. In the x direction, I have only moment frames, correct? In the y direction, I have two moment frames and two brace frames. So in the x direction, I'm gonna call it moment frame building. In the y direction, I'm gonna call it dual system building, if you like. So now we introduce something new, which is a dual system. So now we understand that this plan here, in both directions, I have dual system. Because in the x, I have two moment frames and two brace frames. In the y direction, I have also two moment frames and three brace frames. So now it makes sense. Now I understand that I have in our project is going to be a dual system. I don't have a building frame system or a moment frame system in our project. What I have dual system in both x and y direction. Like in this case. In this building, I have dual system in x and y. How's that? Here's the x. Moment frame, brace frame in the x. In the y direction, I have moment frame, brace frame, and brace frame. Just by looking at this, I guess I should be able to bring you a plan view very similar to this and ask you, is this a dual system, moment frame system, or building frame system? I'll let you here decide. This can be maybe a good question also. Now let's look here, how do you do here seismic design for buildings? We have two main methods. The first method is called prescriptive design method. Prescriptive means here that you're going to be going through the code, you're going to see some equations, and based on this equation, you determine the seismic forces you impose on your building, in your model, the structural model, you find out the moment values, you find out the drift, and then you do all the code checks, like in terms of strength, in terms of drift, and the whole thing. This is what you call here prescriptive design method. This is good, I'm gonna say, for buildings up to maybe 6 to 7 stories building. After this, you don't wanna do prescriptive design method. Otherwise, the cost is gonna be very big, and most likely it's gonna be tough to make your building work. Once you go to higher buildings, maybe you'd like to go performance-based design method. And in this case, you don't really need to follow the code equations. Code equation means the seismic force is going to be equal to whatever, something like CS multiplied by W. You don't want to do this. Instead, you'd like to come up with some size and then do a check on the strains and the stresses within the building itself. So in this course, I'm going to be covering a little bit of this prescriptive design method, which means a code method, if you like.
Professor, you said the performance base is for higher than 6 or 7 story buildings?
Yeah, it's gonna be more suitable. Once you go to 7, 8, 9 story, 10 story building, it's gonna be more suitable because you can go to smaller sections in beams and columns in steel. And also same thing for concrete. But I've seen 10 story building and they design it with the prescriptive design method, which is fine. I mean, it's gonna be up to them, but the building is gonna be kind of more expensive or heavier in terms of the cost of the lateral system. Okay. Now this applies only to seismic, not to gravity beams, right?
Yes.
Okay.
Thank you.
Any question? Okay, you're done. All right. So I'm going to be covering here the prescriptive, which means a simple design method that you all are aware of. Usually in the code, we're going to be referring here to EGCE when it comes to the seismic forces. And we're going to say, they say that there's 3 analytical design methods or procedures to figure out the forces that you have on buildings. We have this equivalent lateral force, which we called here static force design method, and then we have dynamic and then dynamic. The first dynamic here is when you use the response spectrum. So if you decide here, I'm going to go back here for quick. If you wanted to use this response spectrum that we have gone through already by finding out natural period and then find out the spectral acceleration divided by R factor, it means that you're doing here dynamic analysis, just, you know. This considered to be a dynamic analysis method. So I'm going to go back here. So now I understand this model response spectral analysis. If you like to do time history or time step analysis, so let me put this here. I'm going to say this is here called seismic response history or time step analysis. This is going to be really tough. This guy take long time before you are done with it, just because it's going to be very critical. So usually people would like to use a static or this dynamic, one of these two. So I'm going to say it's going to be this or this. In this table here, it gives you some information about the building. It's going to be some structural characteristics of the building, which means building information. You can call this building information. And then you're going to say, if you like to use a static, it's going to be permitted, and all of a sudden you go here, not permitted. So P means permitted, and P means not permitted. Permitted, which means any building is going to be, of course, okay to do it with this time step analysis or time history analysis. If you like to, of course, this is going to be okay. If you like to do this model response, which means dynamic analysis with the response spectrum, it's going to be allowed. Any building is going to be allowed. The problem, if you like to simplify it and do the static force procedure or analysis, right? There's certain type of buildings that you don't want to do it with it, which means once you come here to certain irregularities, you don't want to do this. And once, of course, you go to certain height, you cannot really do the static analysis. And you can see it there. If you say here, when the building goes above 160 feet, and with this natural period, so you have some limitation, you cannot really use, I mean, once you go beyond this, you're going to be in this not permitted for the static. Our buildings that we have in our project, how many stories was it? Anyone recalls? 3 stories, I guess. Was it 3 stories? Am I correct? Yes? No?
Yeah, 3 stories.
Yeah, 3 stories. So I don't think we're going to be beyond here 160. And I didn't give you any irregularity. So in our project, we're going to be using static analysis. So, okay, good. At least now I know. When you look here also at the EGCE 716, we have this main equation for seismic. I'm sure that you guys heard about it. Anyone here didn't hear about this equation or he doesn't know how to use this equation? Has everybody heard about this equation and knows it? Yes? No?
Yep.
If you don't know about this equation, please let me know. Otherwise, I'm going to assume that everybody knows this seismic equations very well.
Could you review it for us?
What?
Could you review it for us? I
Yes,
think I
I'm going to be
remember
going
it,
through
but
it,
I want to make
but
sure.
you have taken it, right? Which means that you know where to find it. I just want to be sure about this.
Yes.
Okay, very good. All right. So let's look at this equation. It says that the total shear, which means the total seismic force on the building. Why do I call it shear? Because if you add all the forces to each other, if you sum it, if you do summation of all the forces, right, acting on the building is going to be equal to the base shear from the other side. This is why we quote here the base shear in the code. It's going to be equal to some seismic coefficient multiplied by the seismic weight. What is the seismic weight? By definition, in this code section, it says going to be equal to the self weight of the building plus the following. So you have 4 items here that you need to add. If you have a storage occupancy, what's the storage occupancy? Storage occupancy is going to be different from an office storage or residential storage. So if you have an office and you have one room, it's going to be called, let's say, storage for supplies and whatever. You don't call this to be a storage load. Storage load when the whole building, entire building, or entire level, or let's say half of the building is going to be used for storage. And this load is going to be at least 125 PSF as in life load. So in our project, we don't have that. It says here is give you the partition weight as you calculate out, which means if I give you here a plan with some partitions, you figure out the weight of the partitions per square foot of the floor plan. Or you simply use 10 PSF. Now you feel that we are using the partitions as what? As dead load. So previously, we considered the partitions to be life load as 15 PSF. Now I'm saying partition is going to be dead load, is going to be 10 PSF minimum. And then if you have some permanent equipment on the rooftop, like what? Like for example, you have an AC unit on the rooftop. So we need to assume here for our project that we have certain amount of AC units on the rooftop. Also, if you have any generators, if you have any permanent equipment, as it says here, then you need to consider it as part of the seismic weight. Also, if you have snow load, we don't have it on our project, but if it happens, you take 20% of it when P of the floor or of the roof is going to be equal to 30 PSF or more. So we don't have this. We don't have the storage load because we have an office occupancy. And we don't have this. So we have permanent equipment. I'd like to hear from you guys in our project. How much should we consider for the permanent equipment on the rooftop of this building? I'd like to hear suggestions from you.
Get the weight of equipment from manufacturer catalog.
Do you know which weight, Mr. Mohammed? Do you know what equipment we're going to be putting there?
We should see the mechanical and the plumbing drawings.
Do we have mechanical drawings? Don't think so. Right?
Yeah, but to be precise, we need.
I mean, we're starting our design. The mechanical engineer is still working on his project, right?
Mm-hmm.
So we need to throw something there.
So we can estimate it like.
Yeah, like what? How much you think this building?
Usually 10 PSF.
10
10 to
PSF.
15 PSF.
Okay, now I'd like to put a number like in kips or pounds total.
2 kips.
10 kips. All right, I'm gonna go with 10 kips. Who said that?
I said 2.
Two kips. All right, Jonathan. This is very close. Only a factor of 5. You're good. It's very good. That's fine. So I'm gonna put there 10 kips, maybe about 10 kips for this building, right? Did you guys copy that? So I don't want someone to come here when we're grading your project and say, hey, I don't know where did you get this number from, right? Now, all of you guys, you know about it. I know some of you may be awake, some of you may be not giving enough attention to me, but we covered it. This is gonna be for the equipment. I said, okay, good. So how about in our building here, if I'm looking at one of our buildings, like in this case, let me put it back, I'm gonna say here, okay, because I need to have the load criteria, right? I need to figure it out. No, this is not the one. I have lots of files open now. Okay, let's give you this guy. I'd like to figure out the weight for this building. I guess I should be able to figure out the square footage of this building. Someone's gonna say, how can I figure this out? Do I need to calculate out the entire area and do all of these cuts or do deductions and additions, stuff like this? You can say, you can do this if you want to, if you have enough time. But for me, for example, I just ignore this piece, instead also ignore this void area, right? Just consider it to be infilled. How about the elevators and this opening? Should I just deduct them or just consider it to be infilled? How do you guys feel about this?
Infill is easier.
Yeah, just consider it to be infilled. How about the elevator? Someone's gonna say, how about the elevators? You have an opening here. I'm gonna say, just ignore it. Don't worry about this elevator because you're gonna have a weight for the elevator that we disregard. How about this for the stairs? I say for the stairs, just ignore it. Consider this to be infilled, right? No deductions for any of these openings, right? Because now I'm doing what? The seismic weight of the building. How about this piece here? You say this piece, you know what? If you like, just consider this piece, ignore this one. It's gonna get canceled with this and this. So just add this piece, and then here is gonna be up to you. So I'm gonna say, you know what? Just add this piece here, or maybe this. Disregard this, disregard this. So it's gonna get canceled out. Does it make sense?
Yes.
And
So
with that,
you're
you're gonna
kind
have
of
this.
rounding.
Yeah. So with that, you're gonna have the square footage of this floor plan. So you need to come up with this. So you have all of this distances or length. You can just figure out the floor plan. Make a number, a good number. Don't give me a fraction. Let's say someone find out, I'm just throwing this number here. Let's say 13,254 square feet. Would you go with that? I'm gonna say, you know what? No. This is actually, I'm gonna consider it to be 300. Does it make sense? Just make it a simple number. Don't make it complicated. Don't give me fraction. Anything less than a foot, right? It doesn't make any sense. Just remember this. Make it simple. So go to the closest, I'm gonna say maybe 100 square feet. Are you guys following me? To the closest 100 square feet when it comes to the building size and weight. And for this one here, we're gonna have the weight of the metal deck, the weight of the concrete slab, the weight of the steel beams as an average. So as an average for the weight of the steel beam, so I'm gonna say here steel framing, right? I'd consider 12 PSF. So don't try to carry the weight or to find out the weight of this beam is gonna be 44 times the length and then divide by the spacing. Don't do that. Otherwise, you're not gonna finish, right? So in your load criteria, you're gonna have the metal deck, right? And what else? Concrete slab. You figure out the weight, right? You have this already that you have done. And then you're gonna have the steel framing. Just take it as 12 PSF. And what else do we have? You're gonna have additional dead load. How much was it? Additional dead load?
15 PSF.
Did I put it as 15?
10.
10
The
PSF?
electrician.
10
Yeah, the
PSF?
equipment.
Okay, this is a small equipment, not the rooftop equipment, right? Rooftop equipment is different, the 10 caps. If you remember the 10 caps, it's completely different. This is just the, let's say like the light fixtures, mechanical ducts that you see, like I'm sitting here in the office, I have mechanical ducts, I have fans, I have whatever, some stuff here, light fixtures, so I'm gonna say this, and also the ceiling, this is gonna be covered by 10 PSF. Anything else that I want to consider? I'm listening to you guys. What else you want me to consider according to this?
The partitions.
Yeah, I'm gonna say partitions. How much?
15 PSF.
10 PSF.
In PSF minimum. I know when it comes to life load, we consider to be 15 for the gravity design. Now I'm talking about seismic design. What else? So we're done with this. We know that this is gonna be in the rooftop, right? Because I added part of it as additional dead load here. Additional dead load is gonna be covering part of this permanent equipment, right? Like if you have a small fans, like air handler units, like small ones. And if you have ducts and stuff like this, I know it's gonna be covered, but I have the big item is gonna be 10 caps. Where? In the rooftop. So it's gonna be only related to the roof. Any other thing that I need to add here? No? How about the exterior scan? Don't you have like on the perimeter here, a heavier wall? Like this facade, exterior facade? I'm gonna say yes. What is the weight of the exterior scan? I'm gonna say exterior skin. How much is this weight? Have we ever talked about it before? Do we have it? In the project criteria, do we have it? Yes or no?
Yes.
Yeah, 20 PSF it's going.
Exterior skin 20 PSF with the exterior elevation. What does it mean by exterior elevation? It means I'm gonna have here a line load, right? You can just consider it to be straight. Don't do like this. It's gonna be too much work. If you like to do the perimeter, it's gonna be just waste of your time. So for me, I just take a box like this. I'm gonna say, how much is this length? How much is this width? Times 2. Just find the perimeter of this box. It's gonna be the same, right? So don't try to figure this and plus this, plus this. No, just do a big box. Look at the total length, total width. Add them to each other times 2. Now we are gonna have the perimeter. So I'm gonna say exterior skin is gonna be equal to what? How can you figure out the weight of the exterior skin? I'm gonna say this actually can be simple because I'm gonna say it's gonna be equal to the perimeter. I'm gonna call it P as in feet, right? Multiply by what? By the story height. And how much is the story height? 14 feet. Am I correct? The story height of our project, for each story I have 14 feet. You remember this? So I have the entire perimeter times the roof height, the floor height, times what? 20 PSF. I'm gonna have here some number as in pounds. Does it make sense?
Yes.
Good. So now I have the total weight of this exterior skin for the entire, for one level as in pounds. So if you like to add it to the load criteria above, you just take this weight, right? Take this weight as in pounds and divide it by what? By area of the floor. And with that, you're gonna have it as in PSF. So you can convert the total weight of the exterior skin as in PSF and add it to the partition, add it to the additional dead load, add to the steel framing, add it to the concrete, add it to the metal deck.
Professor, the area is going to be the area of the big box that you just drew, right?
It could be of the big box, or it could be in the final area that you figure out, because when you started, we said, let's figure out here the total area of the building, right? And then said, you don't really need to get crazy about it. You can just do this little area, ignore this, right? And ignore this piece and ignore this piece, right? Ignore some pieces. So come up with some good area that you'd like to use. Because you see these corners, someone's gonna say, how about this area here? There's nothing here. Should I consider it or I shouldn't? Just say a little bit, yeah, consider it partially. Especially when you take your dimensions, you're gonna take it from the center. Are gonna be considered this piece? This can be like a foot. You ignore this foot, right? Because when you are taking these dimensions, you're gonna be taken from grid line to grid line. Does it make sense? When you add this distance from here to there, did you consider this little bit of an overhang of the deck? You did not. Just like a foot, you ignore this foot. So instead of going crazy after doing this, just take the area here from center to center and ignore this recessed area, right? Ignore this little bit of extension, just ignore this piece, ignore this, right? And add maybe a little bit of an area here, a little bit of an area here to compensate for all of this overhang of the deck. Do it the way you want. I don't want you to spend more than 10 minutes to figure out this area.
Yes.
I'm gonna call it here A, or area. After you find this area, you find the weight of the exterior skin, just find out at the end, it's gonna be W as in PSF, so at the end, so I'm gonna have seismic weight as in PSF. So what do you do after this? Multiply by the total area. Now you have the seismic weight for one level. Now you need to do this for the typical level, and also you need to do this for the roof. Now on the roof, you're not gonna have what? You're not gonna have the concrete slab. Do you have concrete slab at the roof?
No.
Don't have it. So what should I do instead? Oh, I need to use roofing material. How much is this? Do you have it in the criteria? No, I don't have it. How much should I use for the roofing material? Roofing material also is going to include what? It's going to include insulation and this kind of things. So I'm going to be saying, yeah, waterproofing and the whole thing. So how much should I add for this, for the roofing material? 15 PSF. So it is true in the roof that you don't have concrete slab, but you have roofing material 15 PSF. Don't add this roofing material to each level. You add it only to the roof. It says roofing material. You don't add it to the second floor, right? Makes sense. So I'm going to be saying here, you need to start to work on this. Also, I want to show you what's going to happen for the second submittal. What happens second submittal? Here's second submittal. You need to design the connection for the girder. Now you design the girder, but now you need to design the connection of the girder to the column. And also need to design the connection of the beam, the W16 by 31 to the column. Have you guys taken the connection design yet? Did we cover it? Yes or no? I don't know. I forgot. So how's it gonna look like, the connection? Let me open it for you. You need to look at the last example. This gave you the connection design that I'm talking about. So for W16 by 31, how many bolts should I start with? How about for W21 by 44? How many bolts should I consider and what size? So I don't want to write it here, but I'd like to write it somewhere. So at least you know what I'm talking about. So I'm going to write it here for you. And of course, you can see it in the recording. So I'm going to say for W16 by 31, I'm going to be using 3 bolts. So it's going to be 3. I'm going to be using 7/8 of an inch bolts. What type of bolts? I'm going to use here A325N. I want you to try this first. All right. You can say, how about W21 by 44? I'd use 4 bolts. Same thing, A325N. Are you good about this? Yes or no?
Yes.
Okay, very good. How about the column design? You guys, you have studied column in steel, structural steel 1. Do you know how to design the column for the axial load? How do you find out the axial load at the first floor? It's gonna be the other question. So, all right, now I have the spacing. So I'm gonna be taking, let's say, this column. It doesn't say, no, it says intersection of P and 31. Grid line P and grid line 31. Here is 31, here is grid line P, this column here. Can someone help me here and tell me how much is tributary area for this column? because tributary area is going to be equal to this box, right? Roughly, isn't it? How much is the width for this tributary width? I'm going to say this width is how much in the x direction? It's going to be 28 and 3 inches. How about this area here? I'm going to say, oh, I need to do here some math. 24 plus 9 divided by 2. It's going to give me half the way between these two beams. And from here is going to be 28, 28, right? 28 and 20 inches. So it's going to be 29 and 8 inches divided by 2. Half the way from here. Add them to each other, multiply by 28 and 3 inches. With that, you have the tributary area. Now you have the roof load. You have the third floor load, and then you have the second floor load. Do the dead load separate and do the live load separate, and then use the load combinations to figure out the total force on the column at the bottom, right above the foundation. Now try to use a column. It says here recommendation, try W14 by. Now pick the appropriate column for you. Which column size would you like to use here? And do you guys know how to do column design, structure steel column design? In the steel table, do you have it in the steel table? In the steel manual, in the design aids? You have nice charts. It gives you here, for each column size, you have the buckling length, which means in this case 14 feet. So you're gonna say how much is the buckling length for this column? It's gonna be the story height. Put it as 14 feet. And then figure out how much is phi PN. And with that, you're gonna have an answer to this. This should be very short when we come to the analysis and the time needed. We're good? Move forward.
Yes.
Very good. Now we're done here with the seismic weight. Now we need to see the equations. How can we figure out this? If you remember, we have something called S1 and SS, the seismic parameters. And the question is, how can I find them? I mean, someone's going to give them to me. I'm going to say, most likely, I just need to calculate out. But you have the address. No, you don't have the address. So I'm going to calculate them out for you and just give you here these factors. Oh, you have the address here. Good. Can you figure out the seismic factors for this one? For this location?
Yes.
SS and S1? Good. All right. So I'll let you figure this out. Once you find out here, SS and S1, also you need SDS and SD1. Okay, so I'm going to say yes. Now we have SDS and SD1. Also, I need something called here I sub E, importance factor. I need to have the R factor, response modification factor for the seismic. Let me move here to the second equation. It says here T. What is this T? This is going to be the CS that you need to use in your analysis. But it has a maximum value, and this maximum value is going to be based on T natural period. It says here it's going to be for T less than or equal to TL. How much is TL? Let's say for this location, take TL of 12 seconds. Okay, so I'm done with this. At least you know this. Take it as 12 seconds. So most likely your T is not going to be more than TL. So we're going to be using this equation and this equation. Do I need this equation? Most likely no, because natural period of my building is going to be lower than TL. So I don't really need this. And also it tells you where to find out TL. There's a graph for it that you can find it out. Also, I have some minimum values. This minimum value is going to be based on SDS and IE. Most likely, you need this equation just to check it. This one, it depends. If S1 is going to be more than 0.6 G, which means this S1, you know, SS and S1. If it's going to be more than 0.6 G, you need to use this equation. So I say, why not? It's going to happen because S1 in this area should be larger. Now I need to understand this R and I sub E and all these little factors. I need to figure them out. So I'm going to say, if you like to figure out this I sub E, you need to understand which risk category that you're using for this building. We have here 4 risk categories. The second one is what we are going to be using. And it says it's going to be only one line. It's just short, very short. It says here, all buildings and other structures, except those listed in risk categories 1, 3, and 4. Which means if you don't find my building here or there, it's going to be here. And actually, this is going to be most of the buildings that you see around you. Office buildings, residential buildings is going to be right here. So what do we have in one? One is going to be most likely is going to be non-human occupancy. So this one here, non-human occupancy, like it says here, like minor storage, agricultural facilities. The one is going to be there for most of the time. Number 3 is going to be like in the schools. Number 4 is what we call here essential facilities. What are the essential facilities? Like, for example, fire station, right? Calling center, hospital, or some place with maybe emergency. If you have emergency facility, let's say that you have a disaster and you want it to be working, so you're going to be in this category 4. So in our case, we're going to be using risk category 2. Say fine, risk category 2. This is going to be the one I'm going to be using. Yes, to answer your question, yes, it says here submittal 2, but here it says submittal 3. Can I make it here 2 so that you're happy? There's no discrepancy between the numbers. Thank you. Thank you, Maheen, and thank you, Eric, for catching this. Very good. Based on the risk category, I have an importance factor. And according to what we have discussed now, I'm going to be using risk category 2 and give the importance factor of 1. So we're done with this. So let me go back here a couple of slides. Now I understand this I sub E and SDS. You guys will figure it out. So I need to discuss the R factor and the T in the natural period. I need to review it with you. Okay. How about natural period? I'm going to say natural period. You need to do it based on what? I'm going to say based on this assumption here. It says TA, natural period, approximate, is going to be equal to C sub T, some factor, times HN, which means the building height, not 1-story height. So if your building is going to be 3-story, you're going to have 3 times 14 for HN. Now, how much is this C sub T and the exponent X is going to be based on this system here. Now, in our case, do we have a moment resistant frame? Now, this is going to be the question to you. How is the system? Is it a moment resistant frame? Yes? Or do we have a dual system?
Dual system.
We have a dual system. So where do we fall? I mean, where are we at? It says here,
All
steel
others?
moment frame, concrete moment resistant frames, eccentric brace frame, steel buckling restraint brace frame, and all other structures systems.
All other structural systems.
Okay, I have a problem with this because look at this. Ours includes steel frames and eccentric brace frames. And look at the ratio, 0.03, 0.028, exponent 0.75 and 0.8. When you go to all other structure systems, it goes to 0.02. So if you just use here steel moment frame, you're going to be at 0.028. And if you use eccentric brace frame, it's going to be 0.03. Are you telling me if you combine them, you're going to be getting 0.02? Does this make sense? I don't like it. Didn't you?
It's too low.
Yeah, it's very low. I mean, so actually, dual system is not listed here. I cannot really use it here because look at this. So I'm gonna say, you know what? For dual system, I'm just gonna go ahead and use this, and you guys understand the reason. Code doesn't cover this in a very detailed way. And it's gonna be unfair if I'm gonna be using this. This is gonna be 0.028, and if I add here the brace frame to it, 0.03, I'm gonna be lower than 0.02. It doesn't make sense. It should be a number between the two, right? Between 0.028 and between 0.03. And if I have this exponent 0.75 versus 0.8, I'm just going to keep it here 0.8. So let me use here steel moment frame for dual system. And you guys understand my reason for this.
Could we just try both and see which one's higher? I mean, would that be the correct method of doing that?
No, not really, because you need to pick the lower, not the higher. Because look at the T, what the T is doing to your analysis. It is reducing your forces, right? You see here T?
Right, yeah.
the location of T, it is not here, denominator, right? So when you increase T, this is not good. You reduce the seismic forces. If you like to be conservative, you use the lower T to increase the seismic force in your design. So if you like, you can do it with the steel moon frame versus eccentric brace frame, right? And then what do you do? Do the lower of the two values if you want to. I'm gonna be okay with this.
Okay.
And with that, you're gonna have TA. And TA, you can just say TA is gonna be the same as this T. This is fine for now. But for next lecture, we're gonna change our mind because I have detailed example for you how to figure out the natural period in a very good method, right? Without doing lots of computer analysis. We're not gonna do any computer analysis. So okay, now I have an idea about this. Now, I just said that for the 3-story moment frame, I should be able to find out the natural period of it using some dynamic analysis, but without the use of computer modeling. I said, fine. Now, which value to use? This here, it says approximate. This is gonna be like the code equation, right? I'm gonna be using this. So the maximum value, now you'd like to reduce it. The code wants you to reduce the natural period because when you reduce it, you're gonna be having higher shear forces, right? So it is your desire here to increase this natural period as much as you can. But the good says you cannot just use a dynamic analysis and do your analysis to figure out natural period. You're gonna have a limit. Otherwise, you're gonna come up with very high natural period and the seismic force is gonna drop. They say here, your maximum natural period, the actual one that you're gonna be using is gonna be equal to a factor called C sub U times TA. So you don't just do the dynamic analysis, figure out the T actual natural period, and then compare it with T approximate. No, you're gonna have a factor here, some increase. And this C sub U is gonna be given in this chart. It's gonna be based on SD1. So what I did this chart here for you. This C sub U, the lowest value of it is gonna be 1.4. So you're gonna have at least an increase of the natural period of how much? This TA of 1.4 to compare your actual or dynamic natural period with it. I'm gonna show you here some examples, right? We're gonna be going through some examples, but I want you to know that this is gonna be the kind of exact or accurate method of doing the natural period. This one here, it works when you have single degree freedom, which means 1 story only. So if your bin is gonna be only 1 story, this is gonna be the equation that you use, right? If you have 3 stories, this can be the equation that you need to use. So what I want you to do is to train yourself to use this equation because you're gonna have it maybe in your final or maybe second midterm, right? And of course, you're gonna have it in your project. We have a very good solved example on this. I can show it here for quick before we finish our today's lecture. I'm gonna say here it is. It's gonna be in this lecture set number 10. We have example 3, page 11. Here's 2-story. Then you can do this. Then you can do this analysis. This is exactly what you need to do in your project. It's gonna be something like this, but now it's gonna be 3 stories. Instead of having 2 components, now we're gonna have 3 components. If you have any questions, go ahead and ask. Otherwise, please sign out. And I'm gonna see you in, I'm gonna open now the office hour meeting. So please go ahead and type your name and leave.
Thank you, Professor.
All right, thank you.
Professor,
Thank you. Yes, go ahead.
can I ask you a couple quick general questions?
Yes, absolutely.
My first question is about the brace frames. When we were talking about dual system buildings. So I know the moment frames resist the moments and probably the moments that will result as from seismic.
Yes.
What do the brace frames resist?
Same thing, seismic forces. Which brace frame? Let's say this brace frame, right? So when you put an axial force here, right, through the braces, where does it come from? They're going to be coming from this lateral force. So in seismic forces, we're going to be applying a couple of forces here. This is going to be one, and here's the second, right? And
Yes.
the roof, of course, is going to be a little bit larger. So you apply them, and then you solve for the brace forces. And this brace forces, right, is going to be based on this lateral force. And their job here, the brace job, is to resist the seismic force.
Oh, okay. So, so the brace frames, they take the force in the braces that are diagonal,
Yes,
but
absolutely.
not the columns and the beams.
Also the beams and columns, because when you put this force here, you're going to be coming up with some forces. This is going to be the action, not the reaction, right? So this here, the action, this is going to be also the action. So I mean, when you have a force like this, you need to have horizontal component, vertical component, right?
Yes.
So the vertical component is going to be going through the column.
So the dimension of the orientation of the column matters just like it matters in a moment frame, right?
And here,
Like it has to take the force in the
not really, because it's going to be an axial load. No, because here this column doesn't see moment. It's going to be axial load. And this happened in our project. I can show you here our plan. Look at this plan. Look at this brace frame. You have a brace frame in the x direction, a brace frame in the y direction, right? So in the y direction takes the strong direction of the column.
Yes.
And the x direction takes the weak direction of the column, which is fine. Because the column here is not supporting moment. This column supports axial load only.
Okay.
This column here, it needs to be in this direction. It supports axial load and moment. So it's different.
Okay.
From that column.
And for the shear plates on the beams, when we discussed that earlier, is that do we add the plates to make the project cost effective because we only have high shear at the end of the beam? So instead of having a larger section throughout the entire beam, we just add the plate at the end where we have high shear values?
I didn't get that because
So if we look at the shear diagram of the beam, because we have a
this one here
load,
like in here.
Yeah. So it's between sections 2 and 3, we have a plate that's bolted to the beam and welded to the column. Yeah, just right here.
Yeah.
So it's because we have, if we look at the shear diagram, we have high value of force at the end of the beam, right?
Yeah. We provide this only at the end of the beam.
Yeah. So that's why we add the plate only at the end of the beam instead of increasing the section of the whole entire beam. Right, because the web of the
this plate here is to connect between the beam and the column. And it's going to be only in one location. The plate that you're talking about, and instead of increasing the weight, maybe you're talking about this plate, the top and bottom plate. But this plate here has not to do with the size of the beam. It's just based on the reaction, amount of reaction that you deliver to the column.
Yeah. Okay. Yeah. Okay, that's fine.
All right. It seems that we need to talk about this again.
Maybe. I'm actually still a little bit confused about the frame, the brace frames too.
Absolutely. Can talk about it tomorrow. Yeah, come by.
Okay.
We'll talk about tomorrow. I'm gonna be in our office hour. Okay.
I'll try to shoot you an email because I usually have a class at 5:30, so I might not be able to meet the office hours.
Right, just let me know whenever you are available. Just check with me and work it out.
Thank you so much, Professor.
Right. Thank you. Right. Okay.
Professor, I also had a quick question. Is there a way you can also make the midterm review on Wednesday? Because I also have class tomorrow during tomorrow's during your office hours.
Okay? Let's make it Wednesday after the class.
Okay, I'll email you to remind you, but because I know today you're booked, so tomorrow I have class.
All right.
But
Absolutely. Wednesday is good. Wednesday is good. After the class. All right. Okay. Bye.
Have a nice night.
Bye.
Professor, I came late. I want to check the attendance.
What?
I came late to the class.
I know. I checked the end. Yes, ma'am.
Oh, thank you. Thank you.
No problem.
Assalamu alaikum.